and thank you for joining us for a webinar on Benzene and Beverages. Roger giving our webinar this afternoon. Roger came to Teledyne Tekmar over 4 years ago, bringing 30-plus years of analytical method development skills perfected in the environmental, pharmaceutical, and scientific research industries. Since joining the Tekmar team, he has assisted numerous customers worldwide in solving their complicated analytical tasks with Tekmar Headspace and Purge and Trap instruments. He's also the author of over 25 application notes for a variety of complex sample matrices using Tekmar's Headspace and Purge and Trap auto samplers. And just as a reminder before Roger begins, that you can submit questions using the chat function, and so Roger will answer the questions at the end of the webinar. Roger.
Thank you, Shelley. The application lab battle today is between Headspace giants. On board today are Tekmar's Versa and HT3 automated Headspace file samplers. The challenge will be who can detect benzene in beverages at the lowest parts per trillion level possible. The referee will be a GCMS system in a scan mode and you. First, I'd like to quickly review some of the drinking water limits that we found around the world. The World Health Organization suggests no more than 10 parts per billion benzene, while Australia and the European Union have limits of less than 1 ppb benzene in drinking water. Note we set our sights on the 1 ppb limit for the beverages that we tested. Benzene in beverages. In 1990, a lab was using Perrier for their standard and blank preparations and found benzene in that water. They talked to the FDA, and the FDA confirmed that yes, there was benzene in the Perrier. At that, Perrier had to recall many bottles of water. During the time, others were also tested to see if they contained benzene. In the 1990 to 91 time frame, beverage manufacturers and beverage associations did a lot of work to try and answer this question. These found that when ascorbic acid and benzoates were present, low levels of benzene would form when the samples were heated or exposed to light. The benzoate was found to be the contributor of benzene to this process. Many manufacturers reformulated their product, and all appear to be going well. Then in 2005, an independent laboratory tested some beverages from store shelves, found a small percentage with levels of benzene greater than the typical 10 ppb limit for drinking water. This led the FDA to reopen the testing. In 2006, they issued a report they'd performed. The report also included data from different lots of the same beverage and were found to have widely varying levels of benzene. Many associations, including the U.S. FDA, issued reports, some of which included test parameters and methods. One of the complete reports is from the International Council of Beverage Associations. Their document, published in 2006, not included recommendations on how to reduce or avoid benzene formation for the formulators, but included 2 separate test methods. One set of test methods was Purge and Trap, and mentioned the Validity and Solitec at the time. Currently, we sell the Atomics over right. The static headspace. Currently, Tekmar offers these options, the Versa and the HT3. The also has static heads method for beverages. I want to review what is static headspace. Take a sample, place it into a sealed vial with a headspace, and heat it up. Volatiles will reach a steady state between the sample phase and the gas phase. At that time, you take a sample out of the gas phase and inject to a GC. Static headspace is different from Purge and Trap. Trap method, you bubble gas, typically helium, through your sample, and then that comes up through the and out to trap to be trapped. As you can see, with time, you'll exhaust the volatiles in that sample, so you'll have a relatively clean sample at the end of that. With headspace, the needle is placed above the solution. That's then used to pressurize the headspace to a constant pressure. These vials can take up to 30 psi, which is also about 200 kilopascals. This is then used to relay loop back to the same needle, and then that's injected onto the GC system. Because volatiles have reached an equilibrium between the liquid and the gas phase, some volatiles are still present in that liquid phase. Why headspace and not purge and trap? As we showed on the previous slide, purge and trap can exhaust the volatiles in the sample, where the static headspace method will retain volatiles retained in the sample. The ICBA guidance document also mentions that if the sample has solids, static headspace should be used. Finally, we might set out and look at other volatiles that might be present in the beverages. The trap irreversibly traps some of these compounds that we're going to be looking at. Let's look at the contest parameters and some of the results. Standard curve. It's a stock standard following the FDA method. We also had a 0.05 ppm standard to allow us to reach the 0.5 ppb level without having to inaccurately pipette an incredibly small amount of the standard into the solution. The internal standard consisted of a 4.2 ppm solution of benzene D6 in methanol. Prepare a calibration curve from 0.05 ppb to 20 ppb. We did this by taking 10 grams of reagent water in a 22 headspace vial. We then added different volumes of stock benzene solutions, and then added 10 microliters of the internal standard. Next, 8 different types of beverages for the challenge. 4 carbonated sodas, 2 more energy drinks, and 2 cocktail mixes. Labels, while we selected these, 4 had sodium benzoate, 1 had potassium benzoate, 1 had benzoic acid, and 2 none. For the sample preparation, we did them all by weighing it out. We took 10 grams of sample. The carbonated sodas were not decarbonated, as the FDA didn't suggest that, so we used it as is. We trained carbonated beverages by pouring them down a glass rod as shown in the photo. We've also posted a YouTube video of this procedure at http://youtube/OASIEZRGQU, so you can watch this procedure happening. We then also added 10 microliters of internal standard into all the headspace vials. The cautions such as avoiding drafts and such were avoided while we added the internal standard prior to capping the vials. Remember, Benzene is heavier than air with a vapor density of 2.7 compared to air's value of 1. To make a comparison, the loop method of the HT3 was used and the parameters were set the same as the Versa. The FDA and ICBA guidance documents use sample temperatures between 60 to 75 to test the beverage samples, with 70 degrees C for this study. Both sources also use different sample heating times from anywhere from 10 to 25 minutes with and without agitation. We decided on a sample equilibration time of 10 minutes, mixing for 10 minutes, and a final stabilization time of 3 minutes. We also tested the valve pressures to what we should set our pressurization values to. For this experiment, we set the static valve pressure to 12, and then we set loop fill pressure to 9. And then on the next slide, the same parameters were used for the HT3. The valve oven transfer line temperatures were 120 degrees. The sample temperature was 70. We heat sample for 10 minutes. We mix for 10 minutes with 3-minute stabilization time. Pressurization was to 12 psi, and the loop fill pressure was 9 psi. We standard 1 mil loop that ships with both the instruments. Remember, the instruments, other loop sizes are available from 100 to 5 mils, 100 microliters to 5 mils are available. EPA and ICBA parameters were also evaluated, and those these following oven parameters: 60 degrees C for 2 minutes, then we ramped it up 8 degrees C per minute to 150 degrees C, and then it up 20 degrees C per minute to 260 with a final 5-minute hold time. Also set the mass spec up to do a full scan monitoring from the start to the finish of the run, and then we set up the selected ion monitoring from 4 to 6 minutes to detect just the benzene, as that's what we're looking for. With ICBA guidance document, they were looking specifically for benzene, and so that you could separate the deuterated benzene from benzene by their 60-meter column and their temperature profile that started at 40 degrees, ramped up at 5 degrees per minute to 90 degrees, and then did a very quick ramp of 80 degrees C per minute up to 300 to clean off the column. Very similar time, but because we're also going to look at other volatiles to help out labs that may be present in the beverages, the 80-degree ramp may not allow this, so that's why we went with our GC parameters. Operation important. When you compare the mass spectra of deuterated benzene to benzene, there is a minor component at 78 from the deuterated benzene. They interfere with the benzene if those peaks are on top of each other and may give you a false positive. This is also why we chose to use 10 microliters of internal standard instead of 25 microliters of internal standard typically used by the FDA. That's a 10 ppb concentration, and when you're trying to look at sub-ppbs to the PPT level, that can cause some issues there also. Notice, these are the ions of mass 78 versus HT3, showing the blank where you're seeing the small contribution to the mass 78 from the deuterated benzene to the 0.5 ppb standard, which is 50 parts per trillion. Benzene shoulder on the front of the peak was enough to allow the mass spec software to separate these two peaks out and quantitate them. That said, let's look at the linear data for both competitors. The factor for both the Versa and HT3 is below 10%, and linearity is greater than 3/9 for both of these. Let's move on for the samples. The benzene of the samples were very close. It did not contain any benzoate. We did not find any benzene, even down at our 0.05 level. Energy drink that we tested that had benzoic acid in it had a amount very close to our limit of 0.05 ppb. All low level of benzene that we're able to detect, the competitors tied. Yet, no. Part of this also to set up some parameters to evaluate other volatile compounds in our beverages. List some of those. Chromatograms for the 4 sodas. You can see a peak at about 2.2 minutes. As a person developing a method, I may look at this as a peak. This may be a solvent from the flavor agents placed into the beverage. As a person that's in the manufacturing industry, you're always interested in did the correct of a very expensive flavoring agent get placed in the product. This could be done as a test to say that yes, the correct amount was put in because this peak is of the correct size. Looking at some of the other beverages, the same thing. Again, we see this peak at 2.2 minutes, which would be a solvent that was used for extracting flavors from the different natural flavors around the world. Again, this could be used to determine, did the manufacturing process put the correct amount of flavorings in the drinks? summary, the Verse HT3 had linearity greater than 0.95. The Verse HT3 had a response factor percent RSD of less than 10%. And for those of the audience that are in the environmental market, those are very good numbers for benzene. We found that none of the beverages that we tested were above the lowest drinking water standard of 1 ppb. We found that additional compounds could be detected and quantitated by this method. In sum, the Versa and HT3 are versatile economic static headspace autosamplers for detecting benzene in beverages. This is an extremely efficient when the GC runtime is greater than or equal to the static headspace equilibration time. In this example, it is. The HT3, however, is more efficient when the GC runtime is significantly less than static headspace equilibration time. Typical for example, blow alcohols, where the GC runtime is an isocratic 4-minute run, and it may take you 15 minutes to heat up each vial. The HT3 has an overlapping mode that allows this to occur, and samples be injected about every 5 minutes instead of the longer 15 minutes. For our question, the Versa and HT3 automated headspace vial samplers tied, providing great values for the response factors and the linearity. Reference 2 documents in this talk: the ICB guidance document to mitigate the potential for benzene formation in beverages. This is from their first update of the 22nd of June 2006 from the British Drinks Association in London. The document that I discussed was the determination of benzene in soft drinks and other beverages. This was from May 19, 2006 US FDA document from their website. Includes some more drinking water headspace articles that are available at the Teledyne Tekmar website. Include lots of things to detect low levels of environmental toxins of concern in water and other matrices. Thanks for attending today's presentation. At this time, we'll answer any questions that you might have.
Like we said before, if you want to submit any questions, you can do so on the chat function. That's the conclusion of our webinar. Thank you so much for joining us today.